Good afternoon. My name is Ren Hao, and I come from the Harbin Institute of Technology as a PhD student. I'm truly appreciative of this opportunity to present my research optimizing multi-target tracking through airborne passive sensor management. At the very beginning, I must introduce the purpose of my research. We use sensors for information collection and in positioning applications. This information helps us to obtain more accurate state estimates of targets. The term sensors management refers to the process of scheduling the sensor's activity, such as turning them on or off or moving them. In this study, we focus on scheduling the position of the sensors, which aims to improve the accuracy of multi-target state estimation. The information of barostatic range and angle of arrival is used in this research because it circumvents the energy payload resulting from active signal radiation. This means that it can monitor a wider zone in a lighter manner, and furthermore, it's more accurate than other passive positioning methods such as the pure angle of arrival method. We researched the sensor management problem about multi-target tracking in the frame of the random finite set method. It's a famous multi-target tracking framework. Before I explain why we do this, I will introduce a single target BRLA positioning method, which is used in my research as a cornerstone. Barostatic range is the traveling distance from the signal is delivered from the emitter, reflected by the target, and received by the moving sensor. The angle of arrival is the angle between the sensor and the target arm. In the radar frame, we can easily obtain the vector OP and the direction of the vector PI, which means we can easily derive the position of target time by using the cosine theorem. However, there are still uncertainties in the measurements that need to be addressed. So the single target tracking filter model is used to estimate the state of targets, and the likelihood function and the transition density are also implied within the multi-target estimator. We utilize a six-dimensional state vector to describe the target states, which encompasses the target's position and velocity. The uncertainties associated with both the target states and measurements are assumed to be Gaussian. A constant velocity model is employed to forecast the probability density function of the target states, which can also be expressed in the form of Markov transition density. The likelihood function is constructed by linearizing the BRLA measure model using the extended common filter approach, and then the posterior estimation of the target states can be calculated using the Bayesian recursion. Also, we derive the geometric dilution of precision for the BRAOA method and the AOA method, which is written here as a sketch. It shows that the accuracy of BRAOA method performs 2 orders of magnitude better than the AOA method in the edge of this area. A maximum 1.1 kilometers errors versus 100 kilometers errors. With our simulation settings, there's a huge difference. And then I will introduce you about the sensor management method we use based on the RFS. Here's the flowchart of a multi-task sensor management procedure. Sensor management in our search can be described as a partially observable Markov decision process. We have states we have actions, and we have corresponding rewards, and we make a decision by calculating the rewards. In single target situation, we can use the variance to measure the uncertainty of the state, and if we consider the target state as a Gaussian probability density, it's a better accuracy if that density is concentrated with a higher peak and a sharper shape. So what we can do will be like we forecast the single target density. We find out the cost function to describe how sharper the density function becomes after posterior update, and we calculate corresponding rewards with different optional actions. And finally, we choose. When we consider information gathering for a single target, we can find out that as the sensor gets closer to the target, the impact of angle and ranging uncertainties will decrease. That will be pretty easy to understand. However, when we consider the situation of multi-target information gathering, things are not as straightforward. Unless there are other flexible factors such as clutter and misdetection of measurements that can influence the sensor management process. In a nutshell, the reason we do this research is that multi-target sensor management is a more complex and realistic problem to work on. Also, the reason we use RFS method is we can deal with the clutter and the misdetection. We can use multi-target probability density to describe the multi-target states. We use a Bayesian framework. Things become pretty familiar for us to address the multi-target sensor management problem. In our research, the Gaussian mixture probability hypothesis density filter is also used as a cornerstone. Distinguished from the multi-target probability density like this, the oh yeah, like this. Oh. The PhD is actually the first moment of this density. If if the random finite size capital X stands for the distribution of multi-targets, then the PhD is the sum of single target densities, of which the integral value is the number of targets. We use Gaussian mixture to fit the actual PhD. We use the transition function to forecast each Gaussian component of PhD in the step of predict. We use likelihood function generated from each measure to update each component of the PhD in the step of posterior update. And then we extract multi-target state and number from PhD. We choose Cauchy-Schwarz divergence between the predicted and the pseudo updated multi-target probability densities as our reward function, because it's not only a matrix satisfies the triangle inequality, which can measure the information gain by just calculate the CSD value, but also admits a closed form expression and can be directly calculated by GM PhDs. Now let's make a conclusion about our method. First, we predict the PhD, and then we generate pseudo measurements by the predicted PhD corresponding to the actions the sensor can choose. After that, the pseudo update the predicted PhD with different pseudo measurements, and then we calculate the CSD between the pseudo-updated PhD and the predicted PhD. Finally, we choose the action corresponding to the maximum CSD value. Here comes the simulation we use to evaluate our algorithm. We generated 6 different traces with different start times and end times, set the sensor error property like this, and set what commands the Airborne sensor can choose as the table shows. Then we can see the multi-target tracking method we use in this simulation behaves well, and sensor position can be changed as the simulation time goes. We can also see the spatial temporal trend of the sensor trace in the 100 Monte Carlo range, which shows the repeatability of this method. This is a comparison of the multi-target location arrow measured by OSP lock between using the sensor scheduling and not. We can see that the performance has been improved by 8.5% and at about the 450 time interval when the simulation time is 900 seconds. And the solid line stands for the stationary outperform the mobile sensor because at that time there are targets disappeared, and at that time the distance between mobile sensor and the existing targets is longer, which means we underscored the performance of the sensor management. That's all. Thank you for listening.